All right. Hello, everyone. Welcome back to my channel. Today, we're going to be discussing a math problem that seems like it would be very tricky, but once you actually take a look at it, it's actually not as difficult as it seems. So the question that I'm talking about is from the March 2009 comprehensive exam, and it is question number 7. Um, the question is a little bit involved, but let's just read through it together and see what we notice. Let the function f and its first order partial derivatives be continuous on R3 in R3. Suppose that the triple integral over R3 of the absolute value of f of xyz dx dy dz is less than infinity. This just means it's absolutely integrable, right? Compute the derivative d over dr. So we have a new variable r of the triple integral xyz in R3 such that the square root of x squared plus y squared plus z squared is less than r of f of xyz dx dy dz. And then they give us two very helpful notes. It's always a good idea to look at the notes. The derivative should be given in terms of a surface integral. So that's the first thing. And we know that a surface integral is really just a double integral. Another thing to note is that we might want to make a change of variables. Okay, so let's take a look at what we have because there's a lot going on here. And we notice that they're introducing this new variable capital R here, so we can take a look at this inequality. So we have, oh, wrong pencil. We have the absolute value, right, of x squared plus y squared plus z squared is less than r, right? This is really a solid sphere, right? This is the equation of a sphere in 3 dimensions. And so when we see that and they say we might want to make a change of variables, the easiest thing that we can do, right, is to make a change of variables and integrate this surface, right, in terms of spherical coordinates. So there are cylindrical coordinates and spherical coordinates, which are the two main alternate coordinate systems in 3 dimensions. And because we're dealing with the sphere, it's a little bit obvious that we're going to use spherical coordinates. So if x squared plus y squared plus z squared is less than r, that means that we have rho, which is like our 3-dimensional radius, and it kind of looks like a lowercase p. That's going to go all the way from 0 to r, right? And then because we're integrating over all of R3, right, we are going to have phi and theta as their usual 0 to pi and 0 to 2 pi. So phi, I know some textbooks like to interchange these. I always think of phi as the vertical angle, right, that slices down from the positive z-axis. And then I like to think of theta as the one that sweeps the xy plane, much like it would in the 2-dimensional polar coordinates. So that is phi and that is theta. And I apologize because I'm aware that my thetas are very messy, right? So these are going to be our bounds for turning this into an integral of spherical coordinates. And that's kind of our step 1, because once we do that, it's actually quite easy. And we also know that we're going to have to change f of xyz, right? And we don't actually have a specific value for this function. However, we do know that in spherical coordinates, x is equal to, right, rho sine phi, rho sine phi cosine theta, right? So that's going to turn into rho sine phi cosine theta, right? Y is going to turn into rho sine phi sine theta. And z, I believe, is going to turn into rho cosine phi. And these are just formulas that you should memorize when you're converting from Cartesian to polar, right? And then another thing is, right, when you're changing coordinate systems in 3 dimensions, or really any dimension, you want to include the determinant of the Jacobian matrix, right? Because our area is indeed going to be scaled by that factor. So dx, dy, dz, right, which are our differentials, they are going to actually not just turn into d rho d phi d theta, they're going to turn into rho squared sine phi. And this is, again, something that I have memorized. But if you don't, you can also use the determinant of the Jacobian to compute this. D rho d phi d theta. Awesome. So what this is all going to turn into is the following integral. So all of this stuff, maybe I'll make kind of a little cloud bubble around this as well. All of these equations are what we're going to use to make our transformation of variables. And you might not understand what we're going to do after that, but once we make this change of variables, you actually might see what's happening here. Oh, sorry about that. Okay, so let's rewrite our triple integral, right? So this is going to now be this, and we typically do rho, then phi d, then theta, but we're going to switch it up in the next step. I'm going to do it as normal. So remember, rho is going to go from that to that. Phi is going to go from 0 to pi. And then theta is going to go from 0 to 2 pi. F of all of this stuff. And I'm actually, can I be lazy here? I'm not very technologically savvy, but if I could just lasso this and then copy it. Oh, wonderful. That was great. I feel like a genius, even though that was like a very basic skill. Don't come for me. Okay. Right. And then this is going to become, ooh, sorry about that. Rho squared sine phi, right? Because of that Jacobian, d rho d phi d theta. And I have to go a little bit onto the next line, but that's okay. Awesome. And remember, we're eventually going to take the derivative of this whole thing with respect to this new quote unquote variable, capital R. And so I am going to actually, because Fubini's theorem allows us to switch the order of integration as long as you switch the bounds appropriately, I'm actually going to bring that one out to the front, which is totally fine. So it's going to be the integral from 0 to r times the double integral from 0 to 2 pi, right? Pi times the integral, or of the integral from 0 to pi. And then I'm just going to copy and paste all of this other stuff in because that worked for me the last time. So I'm going to try it again. And this time I'm going to do this whole mess. Duplicate. Ah, wonderful. And I'm also going to scale it down a little bit because my handwriting is quite large. I acknowledge that. Okay. And then this is going to be d, oh, wrong tool. This is going to become d phi d theta, right? Theta. And then d rho. All right. So this is what, after transforming the variables, our integral becomes. And remember that we're actually taking d over dr of this whole thing, right? Now, this is where the Leibniz rule comes in, right? Because we know that if we're taking the derivative and it's also in the bound, so if it's here and it's also here, we can actually just substitute it into this equation, right? So it's actually going to be the integral. And because this is with respect to rho, right, we replace all of the rho's with r. And it's as easy as that. So what this is going to become, right, is the integral from this to this, 0 to 2 pi, 0 to pi, f of capital R now, right? So I can't just copy and paste the cosine theta, capital R sine phi sine theta. And that's a theta, not a phi. Maybe I should have been more clear. There. Still doesn't really look like a theta, but it looks a little better. Rho cosine phi. R squared, right? Sine phi d phi d theta. Now, if we take a look at this, right, this f is going to be our function that's in terms of two variables now, right? So this is going to be f of sine phi, f of phi and theta. We can almost think of it like that, right? And then this right here, rho squared sine phi d phi d theta, can almost be thought of as ds, right? Um, and this, right, is indeed a surface integral, right? Because this is kind of the this is the part where we parameterize it, right? We don't have to do that because we don't actually know what function this is / what curve this is being evaluated over. However, this is the form of a surface integral. So I'm just going to write that because why not? So it's going to be f of whatever variable here. It's going to be phi and theta, right? And then times ds, and ds is really, right, our parameterized surface, which is the magnitude of r sub phi cross with r sub theta. And we don't have to do a lot with that, right? We can just leave it in terms of this integral because, again, we don't know much about this parameterization. So all of this is actually totally fine. This can be our final answer. One thing I did want to kind of clarify is this is absolutely not the divergence theorem. So when you have the triple integral, right, and we're integrating it over the volume of a specific region, right, and we can interchange that with a surface integral over a vector field, that is known as the divergence theorem. And that only works under specific circumstances, right? So we have to have a closed surface, and we also need to ensure that the vector field is continuous and differentiable on the entire region. However, right, this isn't actually not the divergence theorem because this is a surface integral in terms of a scalar field. This is f of phi and theta, right? It is not a vector field. So that is an important clarification. While this does turn into a surface integral because the d over dr and the r can kind of cancel out, for lack of a better phrase, it is not the divergence theorem that we're using here in order to turn it into a surface integral. So I know that this was a little bit more tricky of a problem, but once you convert it to polar coordinates, it actually kind of works out by itself. So if you do have any outstanding questions from me, definitely feel free to let me know in the comments about this particular question. If you also want to suggest a particular topic that I cover in the future, I would also very much appreciate that. And without further ado, I hope you enjoyed the video.